Transmitting data over Wi-Fi is in many ways like speaking. You may tell something to a single person or announce it to everyone within earshot. Rules for how loud you're allowed to be depend on where you are, and it's hard, if not impossible, to speak and listen at the same time. So polite conversation partners and standards-compliant Wi-Fi devices commonly take turns speaking and listening. In other words, only one transmission can happen at a time. For devices on a given radio channel, the time available for transmissions, or airtime, is a shared resource, and the 802.11 standard defines rules for how devices should divide airtime between them. But let's say one of those devices is an access point with two connected clients and a stack of data packets in its buffer that need to be forwarded to each client. The AP has to divide its share of the total airtime between each client, and how it does that is up to the AP. If you were an access point, how would you do it? One approach is to alternate between clients, transmitting one packet to client A, one packet to client B, and so on. This straightforward logic is fair in terms of throughput, and it can work well. But it can also go wrong in a way, and to see how, we need to go from thinking in terms of packets to thinking in terms of airtime. The time that it takes to transmit a packet of data can be calculated by dividing its size by the data rate used. In high throughput applications, the packet size will likely be close to the maximum, but the data rates used to transmit to each client can differ by orders of magnitude, either because one of the clients supports a much slower maximum data rate, or just is much further away from the AP and cannot be reached by high data rate transmissions, as those require excellent signal strength to decode. In such cases, an AP sending equal amounts of data to each client will be using vastly more of its airtime transmitting to the slower client. In a sense, the slower client will be limiting the throughput of the faster one. This can be demonstrated with an AP running the older wireless driver package. One of our clients can achieve 42 megabits per second when it's given all of AP's airtime, the other 640 megabits per second. When transmitting traffic to both of them, they each get around 40 megabits per second, a huge drop for the faster device. This can be prevented by dividing airtime evenly between clients. We can do that by upgrading the driver package used on our HAP AC squared, or switching it out for a HAP AX squared, as our Wi-Fi 6 products come with improved airtime allocation out of the box. With the HAP AX squared, our clients can achieve 60 and 1100 megabits per second, respectively. And when transmitting to both of them simultaneously, they each get roughly half of that. This is worse for the slower client, which is no longer getting nearly all of AP's airtime, but much better for the faster client and the total throughput of the AP. In closing, I'd like to acknowledge that starting with the introduction of multi-user MIMO in Wi-Fi 5, it is possible for an AP to transmit to multiple connected clients simultaneously, but instead of dividing airtime between clients, it works by dividing some other resource, such as the number of available spatial streams or channel bandwidth. The main benefit of such operation is reduced latency and protocol overhead. It cannot double our throughput here. I hope you found this more technical video on Wi-Fi informative and interesting. If there are any other subjects you'd like us to cover, let us know. Until next time.